There are three primary ways that you can transform a wave. We've talked about the first two, reflection and refraction, bouncing and bending of light through a medium. Well, today we're going to talk about the third transformation that is common for waves, and that's something called diffraction. Diffraction is light bending around a medium. It's less commonly talked about, but it is equally important and is actually the reason for one of the most famous scientific experiments that we'll talk about today, the double slit experiment. So getting into what diffraction is, it is simply a wave bending around a barrier. And when I say bending, it's not bending in the same way that we saw like refraction bending. In this case, it just operates under the principle that light or sound or any other wave passing through a barrier is going to emit from that area that it passes through as if it was a point source in that location. So for example, if it passes through a gap in a wall, it's going to spread out in all directions in concentric circles as if you were starting a ripple or a wave there in that location. If it's going around a barrier like this, the initial wave fronts over here that are not being disrupted, they're just going to continue on straight as they were. But around the barrier, it's going to extend outward in circles as if that's where the wave was starting. You can experience diffraction right now wherever you're sitting. If there is a light source above you that is casting a shadow, put your hand next to a table or a piece of paper, and you'll notice that the shadow of your hand is not a sharp line shadow, that the edge of the shadow is fuzzy. The fuzziness of that shadow is diffraction in action. Ooh, that's a cool rhyme. Diffraction in this case is the light bending around the barrier of your hand and bleeding a little bit into that shadow to make it not a sharp line anymore. You can also experience diffraction with sound. If you were sitting behind a pillar, you could still hear the sound, or if you're standing behind a wall kind of next to a door, you could still hear what's going on in the hallway even if you don't have a line of sight, because the sound wave is able to bend around that barrier. So let's get into one of the most famous experiments related to light, and that is the double slit experiment. It kind of starts with this question: what would you expect if you had a light source and you shined it through two vertical slots? What would you expect the image to be on the other side? Well, the common conceptual guess of what that image would look like is something like this. You would expect it to be basically just an image of whatever the shape was that you shone the light through. Well, it turns out that that is not what happens. So to see what happens, let's head to my garage and try this out with a laser and some really, really fine grating double slits. I'm going to take my green laser here and shine it through this grating that has very, very tiny slits in here. They are vertical slits, and let's see the pattern that it produces out the other side. If I shine it through two very, very close together slits here, and again these are vertical slits, we produce this pattern that spreads out. As I'm backing up here, you can see spreads out left and right. You can also see bright spots and dim spots. This is your classic double slit experiment and the pattern that's created with the constructive and destructive interference. So I was shining a laser through slits that looked not too different than these. They were just smaller and closer together, and the resulting appearance wasn't two vertical lines. Instead, it was a horizontal line that spread out that was kind of like a dotted line with bright spots and dark spots. Let's talk about why, because that is a surprising result unless you can draw a picture of what's going on and why diffraction is important. So, to get there, let's remember our conversation when we talked about sound waves and interference. If we had sound waves being produced at different lengths, so different path difference here, we could have constructive interference where the amplitudes lined up, the crests and the crests, or the compressions and compressions, or you could have destructive interference that results in just this uniform pressure wave. And depending on the path difference, I was getting these different patterns. Well, If you were sitting somewhere that you experienced a compression from both waves at the same time and a rarefaction from both waves at the same time, you would experience constructive interference. So those waves amplify each other. If instead you're in a place that you have a compression at the same time as a rarefaction, or a crest at the same time as a trough, you get destructive interference. So those cancel each other out. Now, let's imagine that you are using this same concept with two different point sources of your sound. So say you have like a speaker here and a speaker here, and you are standing right in the middle of these two. Well, this location here, this is a constructive interference, that these compressions line up with each other. But with diffraction, we say that if something goes through a barrier like this, it's going to spread out in all directions. So we could really draw these as concentric circles spreading out everywhere to see what's happening in a variety of different locations. So let's just imagine that we're just going to rotate these. This is the same idea as concentric circles, but now in this location here, this black wave actually ends up as a rarefaction, that's a trough of the wave, versus the blue wave is at a compression. Those two cancel each other out. They're not perfectly aligned like we were able to see nicely in the other one where all the dots line up, but we do have low pressure and high pressure at the same time, which is a destructive. If I instead look all the way down here at the bottom, I notice that I have another destructive location here. If I were to continue doing this, if I extended this like way up here, way down below, I would find that I'd find another constructive area followed by another destructive, and so on. The way I would draw this as a transverse wave is something like this diagram here. Now there's a lot going on in this diagram, so let's break it down. First, we have a light source on the other side of this double slit screen. Then it goes through these slits, but because of diffraction at these locations, it propagates outward as if it were just a point source. So propagating outward, I can imagine these transverse light waves going all directions, and in some places, a transverse light wave from both of them ends up as a bright spot because they constructively interfere. The peaks line up with the peaks, troughs line up with troughs. But in other locations, like we saw when we shifted those sound waves, we get peaks and troughs lining up to cancel each other out as destructive interference. These are dark spots. As I keep going, I see these bright and these dark, which then corresponds with what I saw in the garage. That horizontal line that spreads out that way, creating these dark and bright spots as I go because of diffraction and interference. We can see this in water waves as well. If you have 2 point sources creating ripples, we end up seeing areas that constructively interfere and the ripples get really large, and some areas that destructively interfere. I'll let this play out again. The destructive interference is kind of interesting. It looks like a calm water in between these larger ripples. So it's a similar concept here as what we're seeing in the double slit experiment. Another visual of this here, the only difference here besides it being animated is we're putting a screen there and basically saying when it hits the screen, if it is a large wave that they're constructively interfering with each other, that's going to be a bright spot. If it's a wave where there's destructive interference, that's a dark spot. And then going on down there, we're going to see this pattern emerge, kind of this dotted line of sorts. And here's one more diagram kind of showing all of that. So this can be modeled in a variety of different ways, but the same idea is true all over. These 2 point sources propagate outward, creating constructive and destructive interference depending on when they line up. So let's look at how we're going to define this. One of the hardest parts about solving a problem with this is just identifying the variables that are at play. This is the equation that you're going to be given in your data booklet. S is equal to lambda times big D divided by little d. So let's define what these different variables stand for. Well, lambda we've seen before. Lambda is the wavelength. That's the same as what we saw in V is equal to lambda f times lambda, or C is equal to f lambda. Lambda is the wavelength of the wave that is going through. S is the spacing of these fringes. So we would call these fringes bright spots and dark spots, we're going to describe S being the spacing between them. It turns out that that dotted line has equal spacing between every bright spot, the way that it works out on that screen. So we're going to define that as S, the spacing between bright spots, or as it would work out, the spacing between dark spots. Then we have the two different distance measurements. Well, big D, capital D, is the distance between the slits and the screen in which the slits are being presented on, or which these fringes occur. And then little d is the spacing of those slits. So how far apart the slits are from each other. As I mentioned, this shows up in your data booklet right here. And the other biggest component of solving these problems, besides just identifying the variables, is making sure you're using consistent units. Now, the tricky thing here is typically all of these units are going to start out in different places, different metric prefixes. So just as a reminder, if you see milli or millimeters, that'll be 10 to the minus 3. Micro is 10 to the minus 6. And nano is 10 to the minus 9. You can choose any unit to convert into, but I recommend probably just converting everything to the base unit as long as they are all consistent. So let's look at this just in terms of a conceptual understanding of how things change. If we're going to look at how the spacing, how the pattern on the screen changes, there are two main things that we might change about that. Number one is the wavelength. If we increase the wavelength, which basically means we're going from the purple end of the spectrum to the red end of the spectrum, we are going to change lambda here. If lambda goes up, then S has to go up as well. If lambda increases, then so does S, the spacing. If I change the gap, so if I make the gap between my double slit larger, then I'm changing little d. If that gets bigger, then S has to get smaller, so S would decrease. The bigger the gap spacing is, the smaller the spacing in the fringes that are showing up on the screen, the bright spots and dark spots. So let's look at this as a specific problem. Blue laser light of wavelength 450 nanometers is shown on two slits that are 0.1 millimeters apart. How far are the fringes on a screen placed 5 meters away? So just reading through that problem, I notice I have 3 different units for distance. I've got this 450 nanometers. That is my wavelength. I have 0.1 millimeters. That's the distance between the slits. That would be little d. And then 5 meters, that's the distance from the slits to the screen. So that's big D. I want to convert all of these into the same unit. It doesn't matter which one you choose, but I recommend choosing meters in this case. So 450 nanometers. Nanometers is 10 to the minus 9th. So I'm just going to multiply that by 10 to the minus 9th. That would be a very small number of meters, and that checks out. That a wavelength would be a very small number of meters. So 450 times 10 to the negative 9th is fine. I don't need to make that standard scientific notation and put a decimal there. I can leave it as is. Same thing here. Millimeters is 10 to the minus 3, so I have 0.1 times 10 to the minus 3 meters. Then I can leave 5 meters as is. I want to solve this for the spacing of the fringes. That's S. So I just plug this in and solve for S. If I make sure that I'm using my calculator correctly, I highly recommend that you use the capital E notation. So on my calculator, it's second and then that comma to get EE. That's equal to times 10 to the, so I would write 450 E negative 9. That just makes it easier to make sure that you're doing order of operations correctly. Otherwise, make sure you're using parentheses so you're not accidentally multiplying by a magnitude after the fact. This will all result in a spacing of about 2 centimeters or 0.02 meters. The next question is, would red laser light have fringes closer together or farther apart? Well, that's the same as the conceptual things we were talking about on the last slide. If I have a red laser, that means my wavelength has to be bigger. Okay, if wavelength has to be bigger, would S become bigger or smaller? Well, wavelength shows up here. That's the green number here, 450 times 10 to the negative 9th. So if that becomes bigger, then S has to be bigger as well. So increasing wavelength results in fringes getting farther apart. The takeaways for this lesson: you should be able to describe how light bends around a boundary, whether it's a shadow or going through a slit. You can predict the resulting image of a double slit experiment is not exactly what you'd expect. It's not going to be those two vertical bars. Instead, it's going to be this horizontal dotted line as those waves are passing through the slits. You should be able to calculate the spacing between bright spots and dark spots for a double slit experiment, and then conceptually relate the band spacing with wavelength and gap distance according to that equation.